all right? And these coordinates actually what we call the new representation that we learned, presentation of X in W1, all right, in this space. All right, cool. Now, let's try to generalize this to a two hidden layer units, okay? So two hidden layer network. So now it's the same thing. So let's look at this together. So in this graph, we have first the first layer. Okay, so we have W1. So this is the first layer, guys, that we're learning. And then we're adding another subunit. So we're adding here U2 units. So we have unit 1, unit 2, and another unit. So basically, we're making the network into big blobs, right? So this is the first network, and we're adding another unit. So remember, this was our first one unit network, you know, like just a single layer. And now we're adding multiple layers. We're adding another additional layer and multiple units in that second layer. So these are the activation neurons, the hidden neurons in the second layer. So let me write it down. So these are hidden neurons in layer L equals 2. All right. And it's the same thing. So basically, you can see that as a hierarchical representation, it gets deeper, and as also a you know, like a multiple factorization problem, right, guys? The same thing. So we're going from, you know, one dimension big W1, and we're trying to get W2, etc., etc. So here we have the input data. We have, you know, the units of the first layer, all right? And then we have the units of the second layer. And this is the whole feature transformation through the whole network. And this is our whole model when we add the linear combination at the very end. So we call it the fully connected network, by the way, because every single feature input right here, so this is, for example, feature 1, is fully connected to all hidden units in the next layer. And here, every single input right here to this current layer is fully connected too. So basically, you guys can see that, you know, all of these are fully connected. So all neurons in my neural network, all of these guys are fully, completely connected. And that's why we call it a fully connected network. So if we look at this, same thing. So it's quite easy. So you guys can generalize. So now we have actually the form of a general two-layer unit network. So this is, you know, the form of the second layer. So we can express it as a linear combination of the the feature transformations or the feature vector that we learned in the previous layer. So the output of the previous layer becomes so this is the output of layer 1 becomes the input, okay, of layer 2. And that's how we go from layer L to layer L plus 1, right? So it's the same operation. Everything is the same. So this is also the recursive recipe for two-layer units. So we choose an activation function. We construct Q1 single units. So these are calculated using the previous, basically, you know, block, the first layer, and then we simply calculate the linear combination of that. So now in this layer, we are learning the weights for the second mapping matrix, okay? So the second mapping subspace, and that's how it works. So it's quite simple. So now I want you to see this. So what do you guys notice as we make the network deeper, what happens to the shapes or the capacity of our hidden units? So what do we see here? So as you guys can see, we have more diversity, okay? So we have a very nice diversity, which means the shapes have become more kind of twisted and more nonlinear, right? So we have some kind of, you know, vibration, some kind of, you know, twist there, and it captures something more complex, right? So the capacity of the network has increased as we added, you know, another layer 2, and we learned a combination of the first, the outputs, a linear combination of the outputs of the first layer. So you compare this visually. So this is the 10H. This is, when you have one layer. This is when you have two layers. And this is the ReLU. And you guys can see clearly that our hidden units in the second layer, they're learning something more complex. All right, they're learning something more complex. And this shows the hidden units activation patterns or shapes of the second layer. So the second layer captures something more complex about the data than the first layer. All right, so this is what it shows us here. All right, cool. Now, so now we have the same thing. So we have our model. So the model now is a combination of, the final model is W0 plus, all the final layer combinations right here. So if you look at this, so where is it? So this is actually the part where we express the model. So we can express it in function of F1 layer 2, F2 layer 2, FU2 layer 2, right? And this linear combination, now we can express every single, basically unit right here. It could be expressed as a linear combination of elements of the first layer. And you can do this recursively. You can trace it back all the way to the first, layer. So this is impressive. It's like a function of a function of a function. And you're composing different shapes of functions, from layer 1 to layer 2 to layer 3, etc. And all these functions, interestingly, this may capture simple, like shapes. This one will capture, complex shape. This one may be even more complex shapes, right? So it's quite interesting. So this composition allows us to express, like the final output as a recursive combination of multiple previous outputs from previous layers, and you trace it backwards to the very first one. So you can see this mathematically and beautifully. Now let's do a condensed graphical representation of two-layer network. So this is also a similar task. It should be easy for you guys. So I want you also to take a minute and see whether you can figure it out again. So what we have here, we have now two mapping matrices. So we have W1 and W2. So W1, you have the dimensions. So let's write the dimensions together just to make things easier. So it's n plus 1 times, so we start from times U1, and W2 is actually from 0 to U1. So 0 to U1, it means U1 plus 1, right? Times, we have from 1 to U2, so that's U2, right? And this belongs to U2 plus 1, the dimensionality of W3. And here you guys can see that we have the input layer. We map onto this spanning space. So this is the first spanning space. These are the bases of the first spanning space. And these are the bases of the second transformation or spanning space. And this is actually, I'm going to use a different color. This is actually the simple linear combination of the outputs of, the mapping onto these consecutive compositional spaces. All right. So take a minute and I want you to write your y as a function of, like x, right? And all these transformations. And don't forget that we have an activation function here, and I have the same activation function over there. So a minute, and then I'll show you the solution in a minute, guys. So let's look at the answer together. So here, for the two hidden layer unit network, so what we have first, the same thing. So we have the input data, right? And we multiply it. So the input data is x. And we multiply it through, we transform it, we map it onto the new space spanned by, spanned by the matrix W1. So W1 transpose, W1 is the matrix spanning my new subspace. So I linearly project or map my point x onto my new subspace W1. And here it's transposed. So it's like, we're projecting into that. And we're having here what are the dimensions. So W1, we have seen the dimensions below. Just write just to remind you guys, so it's N1 times U1. So N1, N plus 1 U1. Okay, so this is N plus 1 times 1. And then we apply an activation. So that's the first part. Okay, so this is activation. And this is, the activation is applied to a vector. So this is the first nonlinear transformation that we have over there. And then we have W2 transpose again. So W2 actually, the transpose should have U1 here. And we're going to have U2 here. So let's see if we have an external bias or not. So W2 is actually U2 and U1 plus 1. So we needed to have actually plus 1 over there. That I forgot. So plus 1. Okay, so just to make sure that the dimensions, because here it accounts for the bias. So, and you can see it in the linear layer. So this is for the bias. And then what we're going to have at last, after we apply W2, so the second mapping space. So my space is getting smaller and smaller and smaller. And this is my new subspace with lower dimensions. So we have fewer spanning vectors. So U2 should be smaller than U1. Okay, smaller than the original features D, right? And then here we apply the activation function A. So this is where we apply it. So we apply it to all of this block. So this block right here is over here. So we get the second linear transformation. So this will give us actually, what will it give us? The F of, the second layer, all right, of my point X. Right? And then what happens is that we take this, second transformation, the new representation of my point, and we combine it, like we multiply it by this, vector W3, that's a linear combination. So W3 transpose. So what's the dimension here of this transpose? It should be U2, right? 1 times U2, so we can have consistency. So basically, which means that W3 belongs to R U2, okay, times 1. And that's my mapping, the final linear combination vector that will get me into this. So you guys can see also, we can write it here. So the output of the first layer is A, W1TX. So this is the first part. So the output of, as I've written before. So this is the output of the first layer. And then we have the output of the second layer, which is this one, the second activation applied to the previous ones, right? And then we do the final model has the linear combination of all of these transformed layers, okay? Very cool. So now what we're gonna do is we'll try to generalize this to L layers. So let's see how this works out. So here in the last part, it's the same thing. So we have now a huge network and we have multiple layers. So you look at this, you just replicate. So basically it's the same operation that you're gonna repeat multiple times. And we're gonna have, different layers. So you're gonna have L layers. So this is the first layer, the second layer, okay? And then you're gonna have L layers right here. So this is L minus 1, and then this is L. So we have L layers. And in each layer, you'll have a particular number of activation units. So you define this differently. So you have different activation units, and these are the number of the spanning vectors in the first space, U1, mapping matrix 1, mapping matrix W2, and UL minus 1. So this is, the last mapping matrix, the last subspace that we're learning. And then we're gonna get basically a linear combination of that. So the final part right here is a simple linear combination of these deeply transformed features throughout all these layers, okay? So actually it's like, sorry, this one. So the final linear combination. So we have a combination of a combination here. So this is the final linear part. And here we have a nonlinear activation before each layer here. So each hidden layer has a different type of activation, okay? Cool. Now, if we're gonna look at, so the formula is the same, so recursive recipe is very easy, but I want you to look at the capacity of the network. So what do you guys notice? The capacity of layer here, we have L equals 3. So if we have 3 layers, right, you see beautiful, more complex shapes, right? What does that tell us? It tells us that the capacity of the network is higher because we have more diverse functions that we are learning, okay? Or mappings that we learn. And these functions will allow me to transform the data and represent the data differently. So this will allow to represent the data differently at different layers. And the deeper we go, the more complex it comes. So what does that mean? It means, like, first, if I look at this, it could be a simple function like that. And then if I move to the next layer, I'm having something maybe like this. And in the last layer, maybe something more complex, right? So which means that this representation, if I look at this whole space, I'm learning more complex representation of the data. And this nonlinear function, right, allows me to simplify. So I can easily approximate any complex mapping from X to Y using these compositions, where I get into a final space by simply using a linear model. We can predict Y. This is fascinating. This is really cool because you're mapping everything recursively through composition into a space where a linear combination, a simple linear combination right here, will give you the correct value of Y, or a very good prediction of Y, okay? So very cool. So that's what I meant in the previous lecture, where, like, deep learning, or it tries to kind of find a space where everything becomes simple and everything becomes easily computable through a linear combination or a linear function. Cool. So now, just to wrap up, these formula, you guys can also derive them easily. The jth element of the feature transformation in layer L, the final model is expressed as a function of the transformed features, the final transformed features in layer L. And of course, you guys know that this could be decomposed also as a summation of, the elements of the previous layer, and you do this recursively, tracing back all the patterns. Now let's look at this beautiful condensed graphical representation of a multi-layer network. So what we have here, basically same thing. So we have our mapping spaces or matrices. So in this case, we have, L spanning subspaces. Okay, so L, we have L layers, and these are actually the spanning subspaces that we learned, okay, to learn, or we optimize, right? And then once we get these subspaces, then we can easily calculate the final, prediction. So what happens here? This prediction, guys, is actually the multiplication. It's the same thing. So you can generalize using multiple layers, multiple weight matrices that we're learning. And it's the same process that you're applying. So you're starting with our data, our data X. And then here we have, W1 transpose until you get to the very first, so we have here actually, like, that's the last one, sorry. So here we're taking X. Yeah, so 1 second. So we're taking X, we're multiplying it by W1, so that's correct, W1 transpose right here. And then you keep on doing that, and you move forward to the graph until you get the very last one, which is here WLT, and the one after that, so it should be WL -1 transpose, okay? And then the linear combination layer, as written over there, is WL +1 transpose. All right, so this formula is a formula of a deep, deep network. And the first one is the first transformation is a first linear transformation. That's this part. And then we apply the first activation. until we get to the final composed feature transformation, which is really complex through this composition rule, and a function of a function of a function of a function, right, of different combinations, and we get our final prediction y of our sample x right here. Okay, so what do we notice? If we remove the a's, guys, it's similar to what? A matrix decomposition, a matrix factorization, right? Just remove the a's, guys. This is exactly matrix factorization. This is the multi-view clustering that we have seen before. This is, you know, the recommendation that we have seen before. So basically, when we remove the a, we remove the nonlinearity, and we have a simple linear decomposition of our data x into basically you know, factors of matrices. So what is novel and what is powerful about deep learning, that it has these activation functions that we added, right? And this activation function is the same. We apply it over and over again, and it allows to better capture nonlinear and complex patterns in the data. Okay, great. Haytham, you have a question? Go ahead.